Welcome back to the second tutorial session on the empirical macro toolbox. Today we're going to talk about VAR and Bayesian VAR. So let me share a screen first of all. And so as I said, we're going to talk about estimation of VAR models. We're going to talk about the classical estimation, Bayesian estimation, and we're going to talk about different identification procedure and computation of different statistics. So as I said, the toolkit or toolbox allows you to do both Bayesian and classical estimation. By default, we're going to do the toolkit does classical estimation and does this by using what is called the Jeffrey prior, flat prior. And the way it's implemented is that given a prior distribution, the posterior distribution is computed, typically with the Gibbs sampler algorithm. So if you want to do simple classical estimation, the function to do the estimation approach is called BVAR underscore. And the BVAR underscore takes as input the data, the number of lags that you want to use in the VAR, and a bunch of options that needs to be specified or not, depending on your approach. And the output is a field called BVAR, which contains a lot of subfields. For example, the most relevant ones for the subfields which are in BVAR are the BVAR phi draws, BVAR sigma draws, which are basically the draws from the asymptotic, in the case of classical asymptotic distribution of the VAR coefficient, the phi, and the covariance matrix, the sigma. There is also draws, there is a subfield with the draws of the error term, which are the E draws. There is another subfield in which, rather than using draws from the asymptotic distribution, it just uses OLS estimates. And there are two functions, which are two subfields, which are particularly important, which is where the impulse responses draws are stored, and as in this case is BVAR ER draws. And this is a four-dimensional object, which has the dimension of the vector variable, number of horizons, number of shocks, and K is the number of draws that you make from the asymptotic distribution. And then there's going to be another subfield which contain the forecast, either without shocks or with shocks. And this is a three-dimensional object. In case you want to use them, there are also information criteria which allows you to choose about the lag length of the model. There is a log marginal likelihood, which is an out-of-sample measure of fit. And there is Akaike, Heiner, Queen, and BIC criteria. You can use basically them to choose the lag length, as is as you will see in one of the examples that is in the tutorial. Typically, by default, you're going to draw 5,000 vectors of parameters and covariance matrices. If you want to change this, you can use the option .k and specify the number you like. And typically, a constant is assumed. If you don't want the constant in your model, you simply specify the option .noconstant equal to 1. So classical estimation is extremely simple. So once you have the data Y, you call this function, everything is stored in this field, and then you select the subfields that you are interested, for example, the impulse responses or the forecast. Now, Bayesian estimation is very simple also. As I said, with an informative prior is the same as classical, and that's the first option you have. You have two extra options, which is the Minnesota prior, which is activated with the option dot priors dot name, and the conjugate normal Wishart, which is activated with the option dot priors dot name. Both of these options need to be obviously specified prior to the calling of the function BVAR, and these are two of the possible options that are included here. If no other options are specified, the Minnesota prior and the conjugate prior are going to be used with the default values. Now, the Minnesota prior is characterized in the toolkit by 5 parameters. There is a parameter we call tau, which measures the overall tightness of the prior. The default value is 3. There is a parameter called D, stands for decay, which measures the tightness of lags greater than 1, and the default is half. Lambda is the sum of coefficient prior tightness, which is how much you want to shrink the model towards a unit root process. The mu is a co-persistence prior, and the default value is 2. And omega is a covariance matrix prior, and the default is again 2. So you can choose these 5 parameters the way you like. You can fix them, or you can optimize. So here are a few commands which allows you to do both. So first of all, as I said, you have to activate the prior with the option prior name, and then you say option Minnesota prior tau equal to 5 if that's what you want to choose for tau, and option Minnesota prior lambda equals 0.01 if you want to choose that. If instead you want to estimate this parameter by optimizing some kind of criterion function, then you need to use the option which is called max min hyper equal to 1. And this is required for parameter estimation. If you set that equal to 1, then you have an additional set of options which set the index of the parameter that you want to estimate. You can choose to estimate 1, 2, or up to 5. And the default is you estimate all 5. You can set up the upper and lower bounds for the optimization. And you can choose among 4 different routines. There are 3 MATLAB routines, which is the minimization unconstrained, fmin onc. There is the minimization constraint of MATLAB. There is the fmin search of MATLAB. And there is the cminwell of SIMS. The difference is that the first 3 are gradient-based methods, and so require derivatives. The last one is a simplex method, so it doesn't require a derivative and could be useful when the optimization function is not well behaved. The marginal likelihood is not well behaved. Now, if you use the command option Minnesota max Minnesota hyper equal to 1 inside the BVAR command, you will be able to optimize. But then it will compute posterior distribution, will draw parameter from the posterior distribution. So if you don't want to draw parameter, you simply want to optimize, there is an alternative function which is called BVAR max hyper. And that basically tells you the toolkit that you don't need to compute posterior draws, but simply to optimize the parameter which are in X. X0, I'm sorry, is the initial value of the parameter. And the optimized parameter are going to be in this vector, which is called hyper. The conjugate normal Wishart prior is activated, as I said, with this option prior named conjugate. And if you don't specify anything else, it's going to choose a normal for the autoregressive coefficient with mean 0 and variance 10. And the inverted Wishart for sigma with scale matrix with the identity and number of degrees of freedom is equal to the number of variable plus 1. If you want to change these options, you have this option prior phi, option prior free mean and covariance, option prior sigma for the scale and the degrees of freedom. Now, these commands that I just described typically are used for estimation of models in which all the variables are endogenous. Occasionally, you may want to use exogenous variables, which are not simply constant of or deterministic trend, in which case you are going to estimate what is typically called a var-x model. The toolbox allows you to do this by using the option.controls equal to x, where x is the vector containing the exogenous variable. You don't need to do anything else, basically. Once you specify the variable x and you use the the function BVAR underscore, it will estimate the var with exogenous variable. And you can estimate the model either with classical, flat prior, or Bayesian methods, both of them. You can use the conjugate prior, but not the Minnesota prior. You can use more than one x. So if you have more, two variable, or if you want to use the lags of the same variable, you simply specify as different columns. And the responses of the endogenous variable to shocks in the x are stored in this matrix, which is called BVAR IRX underscore draws, and is a 4-dimensional matrix. If x is more than one dimensional process, then what is recorded here is the responses to a Cholesky decomposition in x. So in the tutorial, which is now going to be called BVAR tutorial, there are 3 programs which you can play around with. One is the classical VAR, which calculate the optimal lag length of the Gertler and Karady model, and then computes Cholesky decomposition and variance decomposition of a monetary policy shock. The second program is the example 2 Minnesota, which uses Minnesota prior with hyperparameter optimization. And the third example is the var-x, in which a model, a 4-variable VR for the UK is estimated, where the US interest rate is taken as exogenous and the shocks to the US interest rate are considered. The impulse response function can be computed for any specification of priors. So you can use a flat, Minnesota, or conjugate. They are stored, as I said, in a 4-dimensional array, which has the number of variables, the number of horizons, the number of shocks, and the number of draws. If you don't specify the horizon, automatically is computed for 24 period ahead. If you want to change that, you can use the option dot horizon, and then you specify whatever number you want. As I already mentioned, in the case of a Cholesky decomposition, they are stored in a matrix called bvar.er underscore draws. For other identification scheme, which you will see in a second, there are other matrices which are used. If you want to use identification procedures which are different from the Cholesky, you need to specify in the option input that we have seen before launching the BVAR. There is a command to plot the impulse responses, and it's called plot ERFs, which take the 4-dimensional arrays that you want to plot. In this case, generic name is IRF to plot. And there's a bunch of options here which allows you to customize the plots. For example, it's going to put variable names or variable shocks in the graphs. It's going to put 1 or 2 highest posterior density set. It allows also to add other impulse responses. Suppose you want to compare the impulse responses you computed in one model versus the impulse responses you computed in another model. You can add them to the graphs here. And the last simply tells you where you want to save the the impulse responses or the format of the plot. So what kind of identification restrictions are allowed in the toolkit? Well, basically many. So apart from a Cholesky, we can run long-run identification restriction, which are activated with the option .long_run_arf equal to 1. If you use this, then the first variable in the y vector needs to be in log difference. And by default, if you use the first variable in log difference, the first shocks has long-run effect on the first variable. And the basic setup follows the paper by Jordi Galli 20 years ago. Now, if by any chance you want to compute more than one shocks, which are you want to calculate or extract more than one shocks which has long-run effect on the vector y, then you simply need to have more variable in first difference. So if you want 2 shocks, you specify 2 variable in first difference. Now, the impulse responses, when you use this option, are stored in a different matrix, which is called BVAR.ERLR_draws. You can also do obviously sign and magnitude restriction, and you can have a set of restriction at the same time, and this is activated basically using the option .sign parentheses 1, 2, 3, 4, depending on how many restrictions you impose, equal to something. And the something needs to specify the variable at which you want to restrict. I'm sorry, the impulse responses that you want to restrict. A is the variable that you want to restrict, B is the horizon, and C is the shock. So the syntax here means I want to restrict the impulse response function to a shock in C, to the response in A, in variable A at horizon B. The language here, the syntax is pretty flexible. You can use, for example, the same kind of things, same kind of language to put the restriction on elasticities. So here, for example, we take the ratio of the responses of variable A1 to variable A2 in response to shock C, and we say that this should be greater than M. And if A1 and A2 are in log, this is exactly an elasticity measure. Or you can put restriction on the cumulative sum of the impulse responses. So you can say, for example, that the cumulative sum of variable A in response to shock C, the maximum should be less than an upper bound M. The way these sign restrictions are implemented is following the paper by Rubio, Wagner, and Za, and the impulse responses are stored in a matrix which is called BVAR.ERS_sign_draws. Now, more recently, people have used narrative restrictions, where narrative restrictions are sometimes used in conjunction with sign restriction, for example, as in the paper by Antolin Diaz and Rubio. So these are activated with the option .narrative, and the syntax you see it there. It means that in this case, you want the shock V, structural shock V, at time tau, for n period to be shock n. Sorry, you want the shock n to for n period, for tau period to be positive. Okay, you can the syntax is flexible as well, so you can put the restriction not only on the level of a particular structure or shock, but you can put it on the sum, on the ratio, or whatever you want. And here you can also put it on a cumulative sum up to 2 horizons, so tau 1, tau 0, and tau 1. Now the impulse responses in this case are stored in this matrix ERN narrative sign underscore draws. Now one of the most popular approaches nowadays is the instrumental variable approach, which can be activated with the option.proxy equal to the name of the instruments you want to use. And there are a couple of restrictions that you need to satisfy. First of all, the instrument vector cannot be longer than the number of observations minus the number of lags. And the number of the instrument vector is assumed to be ending at the same time of the BVAR. In case they are not, you can tell the toolkits how to line them up with these particular options. Now, one thing that you need to know is that you can allow instrument to be a matrix, so you can use multiple instruments to identify one shock. One thing is that you cannot do is to identify multiple shocks with multiple instruments. If you want to do this, then you have to put a loop in the command. In the impulse response, in this case, they are stored in this BVAR IR proxy underscore draws, and the assumption is that the first shock is the one that you are instrumented. So the four-dimensional matrix in which you third dimension you set it equal to 1 will pick up that particular shock which is instrumented. Now you can combine all sorts of restrictions which are allowed. So for example, you can mix short-run restrictions, you can mix long-run restriction, and you can mix sign restrictions. Okay, the important thing here is to notice that when you use impact restriction, you use Y in the syntax. If you put sign restriction, you put S, and if you put long-run restriction, you put L together with Y. And as I said, you can combine restriction together, and you can estimate jointly. So the presentations that you've seen combine, for example, restriction on impact, sign restriction on impact, plus long-run restriction. And the implementation here follows, I guess, Rubio and Wagoner and Za. So when you use mixed restriction like this, the impulse responses are stored in the subfield called BVAR ER0 sign underscore draws. Of course, the toolkit allows you to compute forecast error variance decomposition and historical decomposition. The forecast error variance decomposition is activated with the command FEVD, which takes the horizon as an input, the matrix of estimated coefficients, the variance covariance matrix, and the rotation matrix omega in case you use one rotational matrix. You can do historical decomposition with this other command. You have a bunch of options here that you can check yourself. And this command does not plot while the forecast error variance decomposition prints. This command neither prints nor plots since there is a lot of output. So if you want to plot the historical decomposition, you can use the following command, the plot shocks decomposition. And you use the output of the series BVAR and the plotting options, which are in the manual. Now, one other popular identification scheme is to use the forecast error variance decomposition to select some shock, and this is allowed given in the toolkit. Basically, you have to use this command, this function, max forecast error variance decomposition. So what this thing does is that it tries to maximize at horizon or for variable I and shock J, given phi and sigma, which are the estimated parameter, the forecast error variance decomposition, tries to find a rotation Q bar, which gives you that thing. Once you have the Q bar rotation, then you can use the ERF response function to basically compute the impulse response and the forecast error variance decompositions that you are interested with this thing. So this is a very flexible tool. It allows you basically to generate impulse responses for any rotation matrix, generic rotation matrix Q, which is not necessarily generated by sine, zero, narrative, or instrumental variable approaches. Now, as I mentioned, the toolkit allows you to do time variation, estimation of time variation, but it's not a parametric time variation estimation. Instead, it is a non-parametric estimation through rolling windows. And there is an example in the tutorials that you can use basically to see, example 3. And it also, there is no specific control to do command to do BVAR with time varying volatility. However, there is an example which is called example 10 VAR heteroscedasticity in the tutorials, which shows you how you can basically account for changes in the variance of the shocks within the structure of the toolbox. So to conclude, there's a third set of exercise that you can try to do practice. They are in the BVAR tutorial again. The first one is the computation of impulse responses with a number of identification scheme, which is in the example 3 IRFs. In the same example, there is also the computation of a non-parametric time varying coefficient model. And in the, as I already mentioned, in the VAR heteroscedasticity example, there is a case which my co-author in particular, an example which my co-author has used to estimate and forecast with the BVAR at the time of COVID, where the volatility of the shocks has clearly increased. So this is it for this second tutorial. Hope you enjoyed and see you for the next one.